here's what we're going to talk about. The TCP/IP protocol stack, which is essential for all networking, IP addressing, and very quickly the binary number systems, binary, octal, and hexadecimal. I'm not going to stress it very much in this semester because it's been traditionally something you need to know, but the more I was thinking about it, I'm thinking it's not that important for the purpose of this class exactly. You'll need it if you do programming. Anyway, all right, so TCP/IP. Oh, here, let me stop this. All right, the point of TCP/IP is to make it possible for computers to communicate. Back in the 80s, I worked in a research lab, and it was so hard to make computers communicate that one of my co-students actually got a PhD just from building a box that made two mainframe computers talk to each other and exchange data. And it was so difficult at that time because each computer manufacturer would write their own proprietary operating system, and then they would write their own protocol to communicate between that same brand of computer, and there was no uniformity to communicate across different brands of computers, so it was ridiculous. And so they created Unix, Bell Labs created Unix, and they created TCP/IP to be the universal language for computers to communicate. And just like a diplomatic protocol makes it possible for countries to communicate even if they're at war, there are rules. You can have an ambassador show up with a bag of stuff you can't search, and even if you hate them, you can't just shoot them, you just have to deport them back home. So even if you're at war, countries can still communicate. It's the same thing here. Even companies that are at war, like Apple and Microsoft, can still cooperate as long as you talk TCP/IP. It's the universal language. So here's the four layers: application, transport, internet, and network. And we'll talk about them. Hey, all right, what have I done? There, okay. The application layer is the one most people see. When you open a web browser or an email client and you see something and type in things, you're dealing with the application layer. That's intended to talk to the humans. That's all most people see. I type in an email, I send it, someone at the other end gets it in their email client. What all the stuff that happens in between is not really my problem. These other layers are what actually takes care of the data to move it from one place to the other. The transport layer contains the most important protocols, TCP and UDP, which are used to package data, and in TCP's case, to make sure it gets there accurately. The internet layer is what moves your data to the correct machine by IP address without worrying about which process on that machine needs to see it. That's the job of TCP or UDP up here. And the network layer is what takes the information from the upper layers and packages it in an appropriate way to move across your network medium. For example, in here I got wired Ethernet going through this black cable, which has certain voltages that have to go through it. I could be going through Wi-Fi or infrared or microwaves or WiMAX or pretty much anything, fiber optics. Then that's all in the network layer of TCP/IP, handling how you really move it down the physical media and how you prepare the signal to put it in whatever format it has to be in to go out the physical media. So here's the application layer. A lot of things that are relatively familiar right on the application layer, like HTTP, so you can see web pages, FTP for moving files, SMTP for moving email, SNMP is for managing routers and other devices on your network, SSH is a secure way to move files and control machines remotely, and IRC, an old-fashioned chat client, and Telnet, an old-fashioned way to control machines remotely from the command line. Looks like we got another. Man, here, come on in. Leave that open. As long as they aren't being too noisy out there. All right. So I've already talked about what these are in simple terms. So that's the application layer where we actually interact with the human user. Then you got the transport layer. The one thing the transport layer has to do is break the data up into chunks. If I write a big email message, it doesn't send it all in one piece. It breaks it into chunks of a certain size. So the data is moving in little pieces, and many different kinds of transport can share the same channel. Usually, your data goes by TCP or UDP. TCP is a connection-oriented protocol, which means when you send something with TCP, you make sure the other end is listening first. You knock on the door, are you there? I'm really here. Okay, then we'll talk. And you also make sure it gets there, so you have a connection. First you have to do a handshake. You really have to know this. This is the three-way handshake. A whole lot of hacking depends on messing with this. So if I want to talk to another computer, I send a SYN, the other computer sends back SYN-ACK, and I send ACK. That's the hello. That's like when you pick up your phone and you say hello, they say hello, now you're ready to communicate. This makes sure that there is somebody listening at the other end and they're ready to get your data. Then I'll send data and they'll continue to X back, acknowledging the data and making sure it got there okay. That's why TCP has a lot of overhead and it can run slow, because I send some data and I have to wait until I get an acknowledgement before I send more. It can be slow for that reason, but it's reliable. If I want to send an email, I know that it all got there, because I made sure they were listening and I made sure they acknowledged every bit that got there. It's controlled by the TCP header, and you need to be familiar with this. Hopefully it's not brand new to you, but if it is, it's the only things we really care about here. The source port and destination port are really important. Those determine which process on the machine is running, is communicating. Because I can have, let me just bring one up here. If I have, if I do netstat, it will show me my network status. It shows me my connections on this machine, and all I have is connections from one process on a machine to another process on the same machine. I'm 127.0.0.1, that's an address for me, and this is just the name of my machine. So that's nothing too exciting right now. But if I open a web browser, like this one, and let me open another web browser, like Internet Explorer, which I normally would never use for anything, but we'll turn it on just for more. I can see there's a difference here. So Internet Explorer is going to go someplace like msn.com. I certainly do not want that to be my default browser. And this will go to my page. And now, if I do that, it will, hey, there I come. Okay. This is a City College website. This is my address. So here it is going to one place by HTTP and another place by HTTP and some more. So I have several connections to HTTP. And the point is, now, this is the local port number. First one is 1223, 1224, 1225, 1226, and so on, because one web page probably comes from several sources. The Microsoft web page has ads that come somewhere else. My page has a counter that comes from MIT, and so on. This is obviously the Microsoft one. So this is how you sort the mail. If data comes in through my network card, it will come to a port on my machine, and if it's port 1231 or 1232, it goes to Internet Explorer. If it's port 1224 or 1225, it's going to go to Firefox. That's how my machine sorts the mail. And the same thing at the other end. These are all going out port 80, which is labeled HTTP there, telling it that I'm trying to retrieve normal web pages. That's why you need TCP ports. And UDP has them too. But right now we're talking about TCP. You have sequence and acknowledgement numbers. Every packet is numbered, because when you send a lot of packets, they can take different paths and get there out of order. So if I have 10 packets, you might get 10, 1, 2, 4, 7, 9, and the others don't show up at all. So you have to respond and say, I didn't get them, and get a resend. The applications at the other end use these numbers to reorder the packets, put them back where they belong. We'll talk more about that later. That's one common trick in hacking. That's one of the things Kevin Mitnick did, was predict sequence numbers and hijack sessions. Then you've got some fields we aren't too interested in here, and here's the flags. The most important flags right now are SYN and ACK. Those are single bits. The SYN bit is either 0 or 1, and this is either 0 or 1, so this byte has 6 important flags in it. 6 bits that can be on or off. The window size just determines how many bytes can be sent before you have to have an acknowledgement, which can slow down traffic, but it's not directly important to us right now. We'll talk a bit more about that later when we get to port scanning. All right, so the critical stuff for us tonight are the TCP flags, starting out with SYN and ACK, the initial sequence number, which is the sequence number in the SYN that makes the handshake, which determines the starting sequence number for all your packets, and the ports, which I've talked about here. All those are things regularly abused by hackers. This protocol was not set up for security. All of TCP/IP was not set up for security. It was invented when the job was to just make it work. They didn't consider about people abusing it until much later. The original only issue of security was to make it withstand normal malfunctions of the devices, broken cables and such. The thought that somebody would deliberately send wrong stuff just to trick it didn't come up. And so there are holes in this that are essentially unfixable. We do what we can to patch it up. In the long run, we ought to move up to IP version 6, but that hasn't happened yet. And until that happens, there will be remain a ton of dirty tricks you can play. So here's the flags. We talked about that. Here's the 6 that matter most to us. SYN and ACK, synchronize and acknowledge. Push pushes through all the data, clearing the buffers. Urgent marks data that needs to be processed quickly. Reset breaks a connection. That's what the Great Firewall of China does. If you go to a forbidden site, like Google is forbidden about half the time, it will then send a gratuitous reset packet to Google saying you hung up when you didn't. This is also how Comcast broke BitTorrent traffic for a while. They would just send a reset, forged to come from you to make the other guy think you hung up. Therefore, in case you're interested, you can make websites that will be viewable in China without their consent by simply setting your web server to ignore reset packets. There are other ways to do it, but that's one common trick used to make websites that will not be filtered by the current Chinese filter. There are better ways to filter, but that's the way they're currently doing it. And the finish flag indicates a normal end to transmission. You didn't just hang up in the middle, you got it all, and you're done, so with the connection, that's what FIN is for. So the initial sequence number is going to be the 32-bit number in the first SYN that starts a connection, and this is the number which starts my packets. Every further packet is going to go up by 1 to keep track of for reassembly. So if I could guess the ISN, I could hijack somebody else's session. And this is the way it was back in Kevin Mitnick's hacking days in the late 80s and early 90s. Early operating systems like Windows 95 would just start the ISN at a certain number, and the next one would just be one more and one more. So the first guy, so all I had to do was connect to a web server and see what ISN it gave me. And if I then call the network administrator and harass him, or I deface the website and then make a call, hey, I just messed you up, or somehow get their attention, so I know they're going to log on right now, I can connect, and I know that I can pretty much guess what number they're going to get, because it'll just be a few numbers larger than the last number I saw. So then I wait until they log in. SYN, SYNAC, ACK, they log in, then I break them out and inject my packets. Even though I don't get their password, I can take over their session that's already authenticated and gain administrative privileges. And that's session hijacking, and it relies on being able to guess the ISN from your ISN. So around 95 or so, all operating systems got updated to fix this. So now they use random ISNs, and if you do an Nmap port scan, which we'll be doing later, one of the things it tells you is it checks the ISN numbers to see how random they are, and it gives you a rating, how random they are and how much luck you're going to have trying to guess them. And if you do it on a modern operating system, it says these are very random, you have 1 chance in 100 million of guessing, good luck. If you get a really old operating system, it's systematic and you can guess the ISN. So, here's the first survey. Now would probably be a good time. How many people did not get an iClicker? Several people came in late. Why don't you come down, bring me an